In this lecture, we will continue with our discussion that we had last time about fuzzy sets and fuzzy reasoning. We concluded with an example membership function like this, which is a bell shaped curve, which is representing some number like close to a. Now, as was mentioned earlier, this can be represented in the computer as a table. For each of these values, for 20 we stored the membership function membership value 0.1, for 30 we stored the membership value 0.5, for 40 we stored the membership value 0.9, for 50 we stored the membership value 1, like that we can go on storing it. There is also another way of dealing with such curves and storing them in the computer, that is as a function. For example, if I ask you to represent a fuzzy set, close to A, the notion will be something, the curve will be something like this, right, where this number is A and any number which is close in this zone, they will have high membership values. So, if I want to store a curve which is of this shape, I can either put it as a table, or I can also find out some function. For example, if I write that the mu of any number, that is say x, any number x in the set close to A, to be represented as 1 by say 1 plus x minus a whole square, then also we will be able to represent this sort of a curve. Just to verify this, suppose this a is 0, suppose this is 0. In that case, mu of, say I am writing as short, close to A, the membership of 1 in that set will be 1 plus A is 0, right. If I assume A to be 0, 1 plus 1 square, that is 0.5. The square part will take care of minus 1 also, because minus 1 will also be 0.5. We can see that the curve is of symmetric nature, all right. Similarly, for close to A, 2 will be 1 plus 2 whole square, that is 4, that is 1 by 5, that is 0.2. So, that is sharply, quite sharply it is falling down. So, instead of storing all the possible values and their membership function as a table, we can decide on the nature of the curve and find an equivalent function which can be computed in the computer. Now, this was given to you as an assignment. I asked you to complete it. I hope many of you could do this. Now, if I really want to have a much more stricter, sharper curve, like instead of that bell like curve, I may like to have some curve like this, all right, or even sharper. Rather sharp here, this sort of curve. You can try in that case that mu close to A of x to be something like 1 by 1 plus mod of x minus a. If you try this, you will find that the nature of the curve is becoming quite sharp, all right. So, we can have either an explicit representation of a fuzzy set which is in the form of a table data structure, or an implicit representation which is in the form of a function. These are the two possibilities of representing a set, fuzzy set in a computer. Now, we usually prefer to have excuse me, we usually prefer to have piecewise linear like triangular, or this is another sigmoid, but it is, instead of being a very continuous curve, it is a piecewise linear curve. This is often preferred because it is easier to represent, and also calculation is easier, it saves the computation. Okay. Next, we come to the notion of linguistic variables. What are linguistic variables? For example, we use the sentences Ravi is tall. Okay. Now, here tall is an adjective, and set of all, in English it is an adjective, set of all tall people is fuzzy. Okay. And statements like Europeans are mostly rich. Now, see, this tall is a linguistic variable, rich is a linguistic variable. Now, here I am in this sentence we are using an adverb which is qualifying this rich. Europeans are mostly rich. Now, how to deal with mostly? That is, of course, just as we have some x and square of x, similar to that, mostly adverb can be assumed to be an operator over this adjective. All right. So, we can define a linguistic variable as a predicate of a sentence and is typically an adjective, okay, which is often qualified by an adverb. This is an observation. A linguistic variable is amenable. In order to be amenable to fuzzy logic representation, must be related to some crisp set on which we can define the fuzzy set. For example, when we say rich, then we may have a crisp set of different possible incomes, and we can define the set rich on that crisp set. Unless we have got some underlying numerical definition of a corresponding crisp set, we will not be able to define a fuzzy set over that. Please note that a fuzzy set is always defined over a crisp set and is said to be a subset of that crisp set, a fuzzy subset as it is said. Now, linguistic variables can be of different types. Usually they are terms, and associated with every term we have got a degree of membership which you have seen, and that degree of membership can be computed through a membership function and some base variables. Now, here is an interesting curve. Here you see that this is the underlying numerical set, crisp set of the different temperatures, okay. And on this side is a membership function of the fuzzy set that we define over this crisp set. So, we can define low temperature as in this way, which we can again translate in the form of a table or some function if possible. It is a piecewise linear. So, I can always have up to 36, less than equal to 36, it should be 1, otherwise it will be a straight line equation with a given gradient up to 37. This is a normal temperature, that means from 36 to 37. So, somewhere in between 36.5 is a normal temperature. Raised temperature, we start from here, and strong fever starts from here and goes up like this. So, you see over the same crisp set we can define different fuzzy sets based on different linguistic variables. So, these are the different terms. Corresponding to each term we will have a different fuzzy set, and there will be a different membership function which defines the degree of membership of the different values of the crisp set. Now, if we have 38 degree centigrade as a particular value, then obviously we will get membership around 0.8, which we can say pretty much raised, and again the same value maps to say in strong fever, it is intersecting in strong fever somewhere here, just slightly strong is our corresponding comment on this membership. So, you see from a crisp value we are coming to a fuzzy value. So, I am getting a membership function, and corresponding to that membership function I can have a corresponding again linguistic statement. Now, there is another term which needs to be introduced, that is called hedges. Hedges are entities which deal with adverb, like John is tall. So, we can define a fuzzy set tall. Okay. So, say this is the height and this is the fuzzy set tall. Now, on this we can say Jack is very tall. Very tall is a further qualification over this, and so that curve will take place, will be like something like this. And somewhat tall is somehow sort of relaxation and will look like this. All right. Now, at this point I would like to mention about two operators. One is the concentration operator and the other is dilation operator. Suppose I have got for some value of x, I have got a membership in tall as 0.5, and the fuzzy set tall will be looking like something like this, right. Now, for a particular height, say this height, which may be 5 feet 6 inches, I have got a membership value something like 0.5. Obviously, for this height the membership in a set very tall should be less. So, intuitively we can think of that the set very tall will be something like this. All right, this will be very tall. Now, according to Zade, it is very convenient to have the membership of very tall obtained, very tall x obtained from this as mu of tall x whole squared. So, this operation squaring is known as concentration operation, and that is reflected in this curve. On the other hand, if we look at the same height and we want to define a set more or less tall, then obviously the membership of 5.6 should increase, right. Intuitively you can think of that. So, that curve will be somehow like this. All right. So, this is a dilated curve, and this is known as the dilation operation. Okay. And this one we can obtain as square root of mu tall x. So, this is one way. So, this square root that is raised to the power half is a standard dilation operation, and squaring is a concentration operation. So, by this concentration operation, this curve will automatically, the membership of this 5.6 in very tall will be 0.25, whereas it in some more or less tall will be quite high, right. So, these are again two very important operations in fuzzy set or fuzzy logic, and this is used to really compute the hedges. The boy is running, the boy is tall, the boy is very tall. How do I handle very tall when I know the definition of the fuzzy set tall? So, that is how the hedges are represented. These are also called linguistic hedges. Now, there are two more important concepts before we move to fuzzy operators. One is set of support. Set of support for a fuzzy set is defined as the set, it is a crisp set of the, it is a crisp set, please note that it is a crisp set of consisting of the elements whose membership value in the corresponding fuzzy set is greater than 0, all right. So, all the elements say height in tall. So, all the heights in the set tall, all the heights which have got a membership value greater than 0 in the fuzzy set tall will be called the set of support for the fuzzy set tall. Another thing is the alpha cut. It is a threshold, that is, we put up some threshold alpha, say 0.3. All the elements whose membership are less than alpha will be taken out of the set. So, if we look over here, we have put in some alpha here. All the elements whose membership value is less than alpha will go out of this alpha cut of the fuzzy set. So, which are the values which will have all these elements in this zone have got membership values greater than equal to alpha. So, only these values will be in the alpha cut of the fuzzy set A, all right, of the fuzzy set A. So, please note that the set of support and alpha cut which are derived from the fuzzy set A will be two different crisp sets, all right. So, this is again the alpha cut. Now, a quick look at probability and fuzziness. So, when we throw a die, all right, then the die can have 6 faces 1, 2, 3, 4, 5, 6, and the probability of each face will be 1 by 6, 1 by 6 like that. But if we say from these dice, if I define a fuzzy set called small number, then 1 will be a small number certainly. So, that is 1, 2 will have a membership 0.5 in this set small number, 3 and all those things will be 0. So, this will be a definition of small. Similarly, this will be a definition of medium, this will be a definition of big number, etc. On the other hand, the probability wise all of them are the same. Okay. So, we must understand the difference between a fuzzy set and a fuzzy number and a probability value. They are conceptually different. Next we come, our ultimate objective is to go towards fuzzy inferencing, which we will do. But in order to deal with fuzzy sets, just as we do in conventional sets, we need to carry out some set operations. So, here we are introducing some fuzzy logic operations, just like and, or, not, which we did in the case of normal set, and for normal logic we will see what they are for fuzzy sets. For example, equality. Two fuzzy sets A and B are said to be equal if for all x their memberships are the same. Okay. The membership of all x in the set A is the same as it is in the set B. Now, look at the difference between this. If in the case of a normal set, we said that two sets A and B are equal if all the elements in this set are equal to this, right. But in this case, say I have got all the elements are same, but this is a fuzzy set and this is another fuzzy set. Unless the membership of this is not the same as the membership of this element, the membership of this is not the same as the membership of this element, and similarly for all the elements, just belongingness will not do, the membership values should also be the same, then only we can say that they are equal. Okay. Other thing is complement. In normal set and fuzzy set it is the same. Complement is here, the complement of a fuzzy set A is denoted as A prime or A complement. Membership of A complement X is 1 minus mu membership of X in A, and that is for all X. Containment, that is A is a subset of B, A is contained in B. That is true in case of fuzzy set if all the membership values for all the X's in A is less than or equal to their membership value of the same element in B. All right. So, you see how we are dealing with now with the membership values. Here are two important operators, union and intersection. The union of two fuzzy sets A and B is defined as a new fuzzy set, where the membership value of those elements for all the elements here will be the max of their membership elements in the individual sets. And similarly, in intersection, the membership value in the intersection set will be the minimum of their membership in the individual sets. Okay. Now, we can quickly give an example to this. Let us see here. That is a very nice example. We are looking at a fuzzy set A. This is a fuzzy set A. All right. This blue line is a fuzzy set A, and then the complement of the fuzzy set is A complement will be this red line is defined by this red line. Wherever its membership, suppose its membership of 20 is something like 0.4, then the membership of A complement for 20 will be 1 minus 0.4. So, it will be 0.6. So, this is the complement set. Look here, we are looking at the intersection. This blue line, this one as I am tracing, that is the fuzzy set A, and this green line is the fuzzy set B. All right, this is B. Then the intersection of them is for all the X's which are common to both A and B, and whose membership value, say I take this 40. 40's membership in A is something like 0.8 and 40's membership in B is something like 0.4. So, in the intersection 40's membership will be the minimum of these two, 0.8 and 0.4. So, it should be 0.4. 50, its membership in A is 0.65, its membership in B is also 0.65. So, in the intersection set, the membership of 50 will be the minimum of this, minimum of 0.65 and 0.65 is 0.65. So, this red line in this way will define the intersection set. The union set on the other hand will look like this. This was A and this green was B, and this union is the red line where I have taken the max of the membership values. 40's membership in B was 0.4 and in A it was something like 0.8. So, I have taken 0.8. All right. So, this is the union fuzzy set. Okay. Now, this we have already discussed that we can modify the meaning of a fuzzy set using hedges like vary, more or less, slightly, and typically vary f is nothing but f square, like tall, very tall, and more or less is the square root of that we have already discussed. Next, we come to a very important notion, that is a fuzzy relation. Now, just to give you an overview of relation, what is a relation? We know that if we have got a crisp set A, in which we have got say Tom and John, and in the set B we have got say marks like 80 and 70, all right. Then we can define a set A cross B, which will be something like all the possible tuples Tom, one element from this and one element from this, John 80, Tom 70 and John 70. These are the possibilities, and we define a relation R, which is a subset of A cross B. So, R may be something like, maybe all the things are not there depending on what R is, Tom 80 and John 70. And now I give a name, marks obtained, a name to this relation. So, marks obtained is a relation Tom got 80 and John got 70. So, that is what we know as a relation in the typical computer science discrete mathematics sense, discrete structures. That is all of you know that this is the definition of a relation. So, similarly, I could have defined, if there was a set C like Mary and Susan, I could have defined a set likes, a relation likes between A cross C. So, Tom likes Mary, John likes Mary. So, that could be a set, that could be a relation, all right. Now, here you see that in a relation, either this tuple belongs to this relation or it does not belong to this relation, all right. From this A cross B, either it belongs to this or it does not belong to this. So, but in the case of a fuzzy relation, this belongingness it will again be fuzzy. There will be a degree or grade of belongingness. So, it will belong very strongly or it will belong very weakly. Now, this relation Tom, John, etc., I can further represent it in the form of a graph, where say I have got Tom and John, and here I have got those marks say 80 and 70, and the graph, my relation was defined as a graph, that is Tom got 80 and John got 70, all right. Now, the strength of these links are 1. Say I can also have another relation, say Tom, John, and there is Mary and Susan, and a relation may be something like this. The relation is likes. Tom likes both Mary and Susan, and John likes Mary. So, this graph can be used to represent the relation. Now, the strength of each of these links, which are denoting the relationship between from Tom to Mary, are all having a strength of 1 in the case of a crisp relation. But in the case of a fuzzy relation, there is a degree of association or degree of belonging. So, we define it as R, the fuzzy relation will be a grade of membership of x, all these elements x 1, x 2, whatever, x1's membership in this relation, x2's membership in this relation in that way. So, this relation is actually associating the membership grade of membership grade mu r of each tuple. For example, friendship. Say Manush and Shuman are friend, they belong to the friendship relationship with a membership 0.9. Manush and Jyoti, well, they are friends, but not that strong. So, that is 0.1. Alex and Mike 0.8, Alex and John 0.3. So, here you see, here along with those ages that we had shown, we are also putting some grade of membership. Next operator that we are looking at are the typical and or not. We know that not of A is denoted by complement of A is 1 minus mu A x. A and B, which is the intersection essentially, is when we have got min, we have got two memberships that x has got for only for the x which element which is there in both the sets, of course, the membership that is minimum in A and B. I take its membership in A and its membership in B and take the minimum. A or B will be the maximum. All right. Now, so if I just take a crisp set that A and B can have only values 0 and 1, this is the truth table. And you see, if I apply min A B for AND, this is the case for AND, all right, 1 1 is 1 and everything else is 0. This is the truth table for conventional A and B. But if I apply mean A B, then also A and B will be 0, mean of 0 and 1 will be 0, mean of 1 and 0 will be 0, mean of 1 and 1 will be 1. Similarly, for OR, the max of 0 and 0 will be 0, 0 and 1 will be 1, 1 and 0 will be 1, max of 1 and 1 will be 1. So, in this way, you can see that the fuzzy logic is actually covering our conventional logic. So, fuzzy logic can be considered to be a superset of the Boolean logic. Next, in order to do some inferencing, what we need to do is we have to look at the if then type of rules. We use fuzzy sets and fuzzy operators as the subjects and verbs of fuzzy logic to form the rules. Now, consider this rule: if velocity is small, then current needed is small. Now, obviously, this is a rule where the definitions are rather or the statements are different than what we had in the case of conventional rules, because here we have got all these fuzzy terms here. So, such rules can be written as if x is A, then y is B. If the boy is tall, then the boy is strong. Now, tall, strong. Now, A, if the boy is tall, then A is a fuzzy set tall, all right. So, where A is a linguistic term defined by a fuzzy set tall, then Y is strong, B is a linguistic term which is a fuzzy set strong defined over some crisp set Y, all right. So, we can have a couple of more examples. If temperature is high, then fever is or this looks a little odd. If temperature is high, then put coolant moderate. Now, here if I write this as if x is a. Now, x is this linguistic term which is taking a value from a fuzzy set A, and that fuzzy set A is the fuzzy set high. Then y is b. Y is the variable coolant and b is again the fuzzy set moderate. So, this is a fuzzy set, this is another fuzzy set. So, fuzzy rules can be generalized in this way. If x is a fuzzy set, then y is b. Now, the question is, if I have a rule like this, if x is a, where a is a fuzzy set, then y is b, right. This is another fuzzy set. Now, I have to evaluate, in order to fire this rule in the form of forward chaining, I have to first evaluate this antecedent, and earlier we found that this antecedent usually evaluated to true or false. Now, if temperature is high, now I have got a fuzzy set high, and suppose temperature is 70 degree, and in the fuzzy set high, the membership of 70 degree is mu of 70 in high is say 0.7, all right. So, this will evaluate to not 1 or 0, but it will evaluate to 0.7, right. So, unlike the conventional rule base where the antecedent was evaluating to true, it is now also having a quantity of truth. I can even make this antecedent a little more complex. Let me make it. Say I now write if x is a is true, then. Now, what will be the value of this antecedent? X is again temperature 70 degree and A is high. So, I evaluate this in some fuzzy set high temperature, something like this, where I got 70 degree, and in that I found its membership to be 0.7. So, this one comes to 0.7. Now, I take that 0.7, I mean this is true. Now, for that, as we had shown in the last class, last lecture, we can define a say some truth. So, here is the mu value of x, mu value of x in high, and there we got say 0.7, and here is a, this is my definition of true, this is a fuzzy set true, all right, it is something like this. So, 0.7 we will have a membership say 0.5 here. So, it is a two level thing. So, this entire thing will now evaluate to 0.5. Okay. This is how the antecedents are evaluated. Now, again we can have some rules like if x is a and just a conjunction y is b, if the temperature is high and the pressure is low, and say as in the earlier case it was 70 and this was high. So, this was evaluated with 0.7 and this was some value say pressure say 56 psi, and in the set low pressure that somehow evaluated with 0.8. Then what will be the evaluation, what will be the truth of this entire antecedent? We have to look into that. We will see that we actually take the mean of these two. So, mean of these two 0.7 and 0.8 will take. So, it will become 0.7. So, we evaluate this antecedent, conjuncted antecedent with the strength 0.7. Okay. So, evaluation of fuzzy rules. In Boolean logic, we know that P implies Q. If P is true, then Q is true. But in fuzzy logic, if P is true to some degree, as we have seen x is A is true with point to the degree 0.7, then Q is true to some degree. It is not just as Q is true absolutely. Like say here simply if P is true with 0.5, then Q will be assumed to be true with 0.5. Now, max mean rule of composition, which I have just now discussed. Suppose I have got multiple rules, there are n observations I mean E1, E2, E3 like that up to En over x, and we have got n different hypotheses for them. Okay. Now, I want to evaluate the max, I want to evaluate the strength of the hypothesis. So, I will take for if all of them are true, I will take the mean of mu, say here this can be a conjunction, right, as we said x is A and y is B. So, there what would we do? We will take the mean of that. So, we will get a mean value of E1, I will get a mean value of E2, I will get a mean value of En, and then out of those I will take the max of those. So, in order to make it a little more clear, let me again write it down. Let me use the same example as I did. X is A, this is the if part, and y is B. Then something, say P is Q. There is one rule. There is another rule, say J is B and K is C, implies R is maybe Q or maybe R is L, something. Now, this one evaluated with 0.7, this one evaluated with 0.8. So, we took the mean of these two and this antecedent evaluated to 0.7. Suppose this part evaluated with to 0.5 and this part evaluated to 0.9. So, I will take the mean of this. So, it will be 0.5. Now, out of this 0.5 and 0.7, I will take the max of these two. So, I will select this rule and I will fire this consequent. This is one approach of doing it. Okay. That is exactly what is being said here, max of all these means. Now, evaluation of fuzzy rules. Most common way is to chop off the consequent. So, we have just now shown the example where we aggregate the outputs into a single fuzzy set which combines their decision. Okay. Now, let us come to fuzzy inferencing proper. There are some things that we need to do for this. The first thing is fuzzification. What is meant by fuzzification? We are given some number. Why do we need to fuzzify? We need to fuzzify because our inference rules are not crisp rules, as we have shown in the conventional rule based expert systems. In this case, our rules are themselves fuzzy. If the velocity is small, then the current is quite small in that way. Therefore, when we get some value, with that value, say the velocity is 5 meters per second. Now, 5 meters per second, is it really small velocity? What is its membership in the fuzzy set small? We have to do, and this process is known as fuzzification. So, we get some crisp value, converting a crisp value such as height, for example, 5 feet 6 inches to a membership value of a fuzzy set such as medium or maybe tall. There are different ways of fuzzification. Some are experimental and some are subjective, all right. And fuzzified values serve as the input to the fuzzy rules. So, fuzzification is converting a crisp value to a fuzzy membership. The other thing is defuzzification. What do we mean by defuzzification? Converting a fuzzy term such as small shift. Suppose something is like some rule is like this. If the temperature is moderate, then turn the coolant control, give that coolant control a small shift. Now, the rule is stating small shift. Now, a robot arm or some automated machine will have to give the small shift, and then for that you will have to actually command it in some crisp term, say 5 degree, 10 degree, whatever it is. And this process of converting this small shift to a crisp value is known as defuzzification. All right. Now, there are different methods of defuzzification such as center of gravity method. Here I show that. Say I have got some fuzzy set like this, any arbitrary fuzzy set, where this is the variable and here is the membership. Now, I get some crisp value after reasoning, say 70. No, I get some membership value, all right. So, I get some membership value here. Now, this membership value will have to be translated to some crisp value. So, this is the process of fuzzification. Now, suppose there is a curve and a curve is of this form, say something was like this, and a particular membership value is actually cutting this curve in 2 points, here and here. So, I am getting this. So, which one will I take? There are different ways. I can take the midpoint of this, or I can take the center of gravity method. That means, for each of these points I take their membership and I multiply them, this value with their membership, and then divide by these values. So, that I get the average of this. So, there are different methods like max, center of gravity method, etc. For those who are interested to pursue this further, there is a very good book. There are a number of books like Clear and Folger, the book by Ross, Timothy Ross, and all these books are very good, and it will be useful to go through them. Now, we show an example where we will be applying this fuzzy inferencing, and let me first explain the problem here. The problem is something like this. We are going to control something. So, we are given some measured value, where I read some value from a plant, okay. I get some numerical value, but my inferencing method is fuzzy. Therefore, first thing that I have to do is fuzzify this and get the linguistic value. Then using my fuzzy rules, I will get some output in terms of linguistics, in terms of say give a small shift or something of that sort. Then I will have to defuzzify that and I will get a numerical value, which I will again feed back to this control. So, here you see I am working at two levels, numerical and linguistic. Now, here is an interesting example. Say there is a crane moving along this axis and there is a container hanging from here, and the control must leave this container at a proper point of time, so that it falls on the ship. It is this, or it takes it from the ship and falls on the trailer. Okay. Now, it is very difficult to model such systems using normal state space approach. Now, here there are two measured variable and there is one control variable. So, what we do in this case, we have got angle and distance are two issues, that at which angle I should leave it and from which distance I should leave it. Now, here you see the container crane, I have to give it a particular power. Depending on the power that I give, the crane will move with different speed and accordingly the angle and distance will vary. So, I have to control that power, that is my objective. So, I read the angle and distance, the numerical values, and then fuzzify it. So, I get not some numerical values, but some linguistic values, and then get the power and then defuzzify it and again actually put the real numerical power to the controller crane. That is the problem that we are trying to solve. So, the first thing that I have to do is to define a set of fuzzy sets, like distance is far, medium, close, 0, negative, close, something of this sort. Angle will be again maybe positive big, positive small, 0, negative small, negative big. Power can be positive high, positive medium, 0, negative medium, negative high, but these are very vague. So, I have to actually define their membership functions. All right. Now, before say I can therefore define the negative big. Here on angle, the negative big is this fuzzy set, negative small is this fuzzy set, positive small is this fuzzy set. In this way I can define it. All right. And given any particular value, say 4 degree of angle, I can find out its membership, that its membership in 0 is 0.2 and its membership in positive small is 0.8. In that way I can find out their membership. So, this is fuzzification. I get an angle and get this membership values. So, this is how I do the fuzzification first. After doing the fuzzification, we will apply the rules. Suppose there are a couple of rules. If distance is medium and angle is positive small, then power is positive medium. If distance is medium and angle is 0, then power is 0. If distance is far and angle is 0, then power is positive medium. So, we need to do two things. First, we have to do the aggregation. That means, first we have to do the computation of the if part, and composition is computation of the then part. The computation of if part we have already discussed, and that is we know about this. Say in the first rule we get the distance medium, in that it was 0.8 and in angle positive small it was 0.9. The angle had a membership 0.9 here and the distance was 0.8 in medium. So, this thing will be the mean, all right, that we have already seen. So, it is 0.8. For the second rule, suppose in the same way the two antecedents gives 0.2. For the third rule it is giving 0.1. So, for each of these rules we do the aggregation, we compute with the mean function the truth of their antecedents. Then I will select do the composition. So, I will come, we have seen all the different rules, that All these rules will give you power to be positive medium, power to be 0, power to be positive medium. So, then when I compose them, I am getting that positive high is not coming with any membership, positive medium with 0.8, because it was the max of 0.8 and 0.1. Where from this 0.8 and 0.1 come? Again, let us go back to this rule. Positive medium, this was 0.8, say the first rule was saying positive medium with 0.8 and the last rule was saying positive medium with 0.1, all right. So, I have got these, so I have taken the max. So, I have taken out of this I have taken the max, so I have got 0.8, all right. Now, with 0.8, what is the power? Positive medium power I have to give, but how would I give that 0.8? So, 0.8 is somewhere here, 0.8 membership is cutting, it is positive medium. So, 0.8 is coming somewhere here. So, I am getting it, I will again compute the crisp value corresponding to this using some method like center of the maximum, and I will get 6.4 kilowatt. That is the power that I will have to give. So, this is the approach that we adopt in the case of fuzzy inferencing. So, summarizing, let me just quickly summarize. Given a set of fuzzy rules, suppose you have got some fuzzy rules whose antecedents are fuzzy, consequents are fuzzy. You have got some value. Then first thing that you will have to do, you will have to fuzzify. In order to fuzzify, you have to define the fuzzy sets beforehand, and those fuzzy sets can be stored as tables or functions. So, fuzzification means you will get some membership value. So, for every rule that is applicable, you will compute the truth of their antecedents. How do you compute the truth of the antecedents? If there are multiple antecedents, if that antecedent is a conjunction, we will take the minimum of those. Now, if there are more than one rules, which are now out of the rules which are applicable, out of this minimum I will take the maximum, and that rule I will apply, okay, and that consequent will give me some fuzzy membership. With that fuzzy membership, say positive medium it is saying, okay, or turn the knob slightly left. In that slightly left you are getting a membership 0.4. Now, you defuzzify that 0.4 is membership is leading to which particular crisp value, and that is the shift that you will give. Now, this approach is rather effective and it is being applied in several applications nowadays.